Alright, welcome back. We're at part 3 of our lecture right now. Now, we have spent nearly half a semester talking about greenhouse gases as a way of changing the climate of the Earth. But it turns out that is not the only thing the humans are doing, the only anthropogenic change that is happening in the Earth's atmosphere that is changing the climate. And one example of that is aerosols. Now, the word aerosol sometimes is something people are uncomfortable with. You probably learned a good definition of it and so on in ATSEVS533. But aerosols are these tiny little particles of solids or potentially liquids in the Earth's atmosphere. And these are very, very small. We're not talking like sand or something like that, or even like dust and lint or something. There are literally several hundred of them per cubic centimeter of the Earth's atmosphere. They have very, very small masses. And they are so small that they generally aren't easily removed from the Earth's atmosphere. Sand, lint, dust, pollen, these things fall fairly fast through the Earth's atmosphere. The right word is sediment. They sediment out of the Earth's atmosphere fairly quickly. But aerosols in the Earth's atmosphere, these very fine bits of ash and soot and salt and so on, are going to take much, much longer, on the order of weeks or more typically, to fall out of the Earth's atmosphere. Broadly speaking, we need to talk about how they get there. Okay? Now, again, in the world of atmospheric science and atmospheric chemistry, people have gotten their PhDs understanding aerosols and how they get there and how they're distributed in the Earth's atmosphere and so on. And the word we use for ways in which these aerosols get into the atmosphere is pathways. There are two main pathways that we can get aerosols into the Earth's atmosphere. One is to actually emit them, like what comes out of a tailpipe of a car, or what comes out of a smokestack, or what kinds of materials come off of a field when the wind blows, and so on. And that's certainly one very important pathway to get aerosols in the Earth's atmosphere, but another is to actually have them form in the atmosphere itself. Atmospheric chemistry is not really my thing, but I totally respect it and understand that it is a big deal. And in the atmosphere, there's all kinds of chemical reactions going on, and some of those chemical reactions result in the production of a solid. Like a little crystal of something or whatever. And that is a way of putting an aerosol in the Earth's atmosphere. You take two gases that are in the atmosphere and you let them have a chemical reaction, and the result is a solid. You get these little suspended crystals and so on, based on their gaseous precursors, to use the right word there. Alright, I don't want to spend a huge amount of time talking about all the different types of aerosols there are in the Earth's atmosphere. That's not my favorite thing. On the other hand, it is useful from a climate perspective to think about, like, broadly what types are there. For example, there are these inorganic types of aerosols that are up in the atmosphere. That is to say, they don't come from life. They're not based on carbon and so on. These are going to be like different sulfates and nitrates and ammoniums and so on in the Earth's atmosphere. Also sea salt. Hold on just a second here. My poor tablet is acting strange. There'll be lots of different ways those can get into the Earth's atmosphere. The ones that are like sulfates and so on are going to largely be from like volcanic eruptions and so on. The sea salt is going to come from the ocean, obviously, as bubbles pop. We'll probably see a slide about that later in this presentation. That is to say, then, that there's, of course, these organic aerosols. There's going to be all kinds of organic species in the Earth's atmosphere. Hold on just a second here. These can be anything from, they come off of fields, they come off of landfills, they come off of, they are the result of chemical reactions among organic gases in the Earth's atmosphere and so on. But they come from life. There's a whole world of biogeometeorology and so on, or biometeorology, where like they study all of the gases and particulate matters and so on that come off of, say, a field or a forest or something like that. Okay, those are the organic aerosols. And that really should be kept separate, and this is where I'm heading with this, that should be kept separate from black carbon, which we usually use the abbreviation BC for black carbon, which is a particular type of carbonaceous aerosol that comes from incomplete combustion of fossil fuels and biomass burning. We talk about the burning of coal or natural gas or something like that, and how it produces greenhouse gases like carbon dioxide in the Earth's atmosphere. But another thing that comes out of your tailpipe, another thing that comes off of your campfire, another thing that comes out of the smokestacks at a coal-fired power plant is incompletely burnt crap. Okay? These molecules are very complicated, the molecules in coal, the molecules in petroleum, and so on, and they don't necessarily completely combust down into their lowest, carbon dioxide, water vapor, things like that. They are still little particles of incompletely combusted stuff in the Earth's atmosphere that are generally black carbon is the right word for these things, and they are very, very fine particles, and they actually have huge health implications and so on. They are very bad when they get into your lungs and so on, but as you're going to see, they also have radiative forcings on the surface of the Earth. Another whole class or type of aerosol in the Earth's atmosphere is actually mineral dust. Various mineral species. This is, stuff that blows off of, say, deserts, dry valleys, sandbars in rivers, poorly managed soils, like if the farmer is tilling the soil too much and so on. Although in practice, almost all of it in the Earth's atmosphere is desert dust. It has to do with the fact of the sizes of these aerosols and so on in the Earth's atmosphere. The ones that tend to be long enough lived in the Earth's atmosphere that they have climate implications tend to be desert dust. About half of all the mineral dust in the Earth's atmosphere comes from the Sahara, and in fact about 10% comes from one particular dry lake bed in the Sahara Desert, the Beaudelet Depression, to use the right word. This just happens to be where sediments of the right sizes and so on, that when they are lofted into the Earth's atmosphere, they last for long enough to have climate implications tend to come from. There's also all these primary biological aerosol particles, or PBAPs. This is stuff like pollen and so on that gets into the Earth's atmosphere. Now, you noticed as I was talking about this, some of these I was glibly just sort of mentioning a natural source of such things. Some I was just sort of glibly mentioning an anthropogenic source of such things, and you probably noticed that some, well, it kind of depended on how you want to think about it. Aerosols that come from poorly managed soil, is that a natural thing? Like that's mineral dust that ended up in the atmosphere? Or is that, well, if we hadn't been messing with the soils, that wouldn't have ended up there? It doesn't really sort out that easily. But broadly speaking, the mineral dust, sea salt, and black carbon and so on are primarily, and also the PBAPs, are typically introduced into the atmosphere as primary particles. They're emitted into the Earth's atmosphere, whereas other than the sea salt, like the sulphates, the nitrates, and the ammonium, are primarily the secondary aerosols that are forming in the atmosphere due to chemical reactions. Now, in the present day atmosphere, the majority of the black carbon in the Earth's atmosphere, the sulphate, and the nitrate, and the ammonium comes from anthropogenic sources. Okay? Stuff we are burning, like in fossil fuels, or stuff we are emitting into the Earth atmosphere, like fertilizers, and so, when we spray them onto the ground and so on. These are primarily of anthropogenic origin, whereas like sea salt and the mineral dusts and the PBAPs and so on are generally considered to be natural. Okay? Yes, obviously, as we change the way we're using the land, we might make it more likely or less likely for there to be mineral dust added to the Earth's atmosphere, but we're not going to really sort it out that way. Aerosols are complicated. Man, the whole business of atmospheric physics and atmospheric chemistry, sorting out this business of what aerosols, how they get there, what they do, how long they last, is a whole complicated thing. But from the point of view of climate science, what we're interested in is how they are affecting the radiation moving through the Earth's atmosphere. And even that's not simple, because aerosols interact with both solar radiation, shortwave radiation, and terrestrial radiation, that is long-wave radiation. If I look down here at this volcano that's erupting, as I'm looking at it from space, I think here, well, you can see that there is some plume of materials being ejected into the Earth's atmosphere, some of which will actually hang out for a long time in the form of aerosols. Well, clearly, this is blocking some shortwave radiation from the sun. If you were under that cloud of ash and dust, you would not be seeing the sun, right? It is optically thick to shortwave radiation, but clearly it also has an effect. It's absorbing long-wave radiation, it's emitting long-wave radiation. Oh man, what a mess. These aerosols are going to be doing all kinds of complicated things. And it turns out what exactly they do, how they are interacting with shortwave radiation and long-wave radiation, that is to say solar radiation and terrestrial radiation, depends very, very strongly on what they're made of, which doesn't exactly seem like rocket science, right? Most of these materials are going to have different ways in which they can interact with the Earth's atmosphere. And radiation passing through it. A key one is sea salt. Sea salt comes from sea spray. When waves crash and little bubbles little droplets of water get spritzed into the Earth's atmosphere, or by, actually most of it actually comes from little bubbles popping in the Earth's atmosphere, and as they, a bubble rises through the ocean, gets to the surface, and it pops. As it pops, it spritzes tiny little drops of liquid water. The water evaporates, leaving behind a little crystal of the salt that was dissolved into the water, and then this becomes an aerosol. Primarily they are from bubble bursting, although breaking in waves, and so it leaves behind this salt crystal that is an aerosol. Actually, any crap that was, excuse my French, but any crap that was in the water, including literally crap, gets left behind. So if that little bubble bursts and tiny little water droplets are hanging out in the atmosphere and then they evaporate, anything from waste products from sea life to desiccated cells from zooplankton and phytoplankton, whatever, it's now suspended in the atmosphere. It's part of what it means, by the way, for the smell of the ocean. Okay, what you're actually smelling is these aerosols, both the salt, although most salts don't have a strong smell, don't interact strongly with how your nose works and so on, and all these desiccated organic crap, including literally fish crap, in the Earth's atmosphere that are also primary organic aerosols. The sulfur aerosols can come from natural sources like volcanic eruptions and so on, but a big chunk of it ends up in the atmosphere due to the combustion of fossil fuels. Many fossil fuels contain large amounts of sulfur. If you look at a chunk of actual coal, we're not talking like charcoal that you buy for your barbecue, but actual coal, it usually has little yellow sparkly things in it. And those little yellow sparkly things are various compounds of sulfur. And when you combust the coal, if you make no plan for what you're going to do with the sulfur just ends up into the atmosphere where it can interact with the gases around it and produce sulphate aerosols. They are actually liquid. They are usually either sulfuric acid droplets or they are precursors to sulfuric acid. Now, the amazing thing about sulphate aerosols is that they have a very high albedo. They reflect a lot of shortwave radiation and keep that radiation from getting to the surface of the Earth. So sulfate aerosols have a negative radiative forcing. In fact, it's negative 0.4 watts per square meter. That is a lot of cooling. I mean, that counteracts just those sulfate aerosols that we're putting up in the atmosphere. Anthropogenic sulfate aerosols are having a radiative forcing on the surface of the Earth of about negative 0.4 watts per square meter. That's about a quarter of the total radiative forcing of carbon dioxide. Yay, sulfate aerosols! Yeah, well, I mean, in the context of global warming, I guess they're good news. But keep in mind that there is all kinds of other problems here. I mean, these sulfate aerosols lead to acid rain, and they are an air quality issue, and so on. We don't, in general, want these sulfate aerosols to be up in the Earth's atmosphere. Now, as it happens, it's less of a climate change in the long run. It's less of a climate change issue than you might think. Anthropogenic sulfate aerosols are mostly in the lower atmosphere. They're put into the Earth's atmosphere by things like smokestacks, which are tall, but they're in the troposphere. And sulfate aerosols are water-soluble. So when it rains, they dissolve into the rain. They make acid rain, which is a horrible problem in and of itself, but at least the sulfate aerosols are out of the atmosphere now. So as a consequence, sulfate aerosols in the atmosphere are not a big problem on like climate time scales because precipitation can remove them pretty fast. Except for the fact that we keep putting them in. So we add sulfate aerosols to the Earth's atmosphere, but they get washed out fairly quickly. It isn't like they're accumulating. Okay? If we clean up our act with regard to how we put sulfate into the Earth's atmosphere, the good news is the effect goes away fairly fast. Certainly within, on the time scale of like a year or so, there wouldn't be any sulfate aerosols in the Earth's atmosphere. Well, government regulations in the West have largely removed, I mean, we don't in general put a lot of sulfur into the Earth's atmosphere from like coal-fired power plants. We have ways that we can scrub the coal beforehand and keep the sulfur from being in the coal in the first place before we burn it, or we have ways that we can scrub the exhaust gases that come off of the power plant and keep the sulfur from ending up in the Earth's atmosphere. These are all good things, but they do mean that we're not putting this carbon dioxide, this sulfate in the Earth's atmosphere so fast anymore, and that had a cooling effect. That sulfate had a cooling effect that we are now taking away. Oh, yuck. By the way, just because it's kind of interesting, when volcanoes put sulfur into the Earth's atmosphere, it primarily goes up into the stratosphere. So stratospheric sulfate aerosols, there's no precipitation up in the stratosphere. They are long-lived. In general, those sulfate aerosols in the Earth's atmosphere, when they come from volcanic eruptions, last years. And like, for example, here's a nice little graph that I found that shows the amount of solar radiation getting through to the surface of the Earth. And you can see that when different big volcanic eruptions have happened, like El Chichon in the late 70s, early 80s, and Mount Pinatubo in the early 90s and so on, there is a real climate radiative forcing associated with that. The volcanic eruptions serve to cool the surface of the Earth because they put sulfates in the atmosphere that reflected shortwave radiation. And those, because they were in the stratosphere, they lasted on the order of at least a few years. Cool. But, you know, just the sulfates that we are putting into the Earth's atmosphere right now do have this net cooling effect on the planet. It's not so much the United States or Western Europe anymore, it's mostly China and India. We're going to see what that ends up meaning for us later. Now, what about black carbon? Black carbon, you know, is that aerosol that's due to the incomplete combustion of fossil fuels and so on. It is an extremely fine black powder. Very, 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 very small materials here. And these aerosols can hang out in the Earth's atmosphere. And as the name suggests, it's very dark. It has a very low albedo. It absorbs shortwave radiation. So if you put black carbon into the Earth's atmosphere, you have made the atmosphere better at absorbing shortwave radiation. Radiation that might have otherwise been reflected back into space or something like that. The net radiative impact, the radiative forcing of black carbon that we put into the Earth's atmosphere is about 0.2 watts per square meter positive, meaning that, you know, it is serving to increase the temperature of the Earth atmosphere system. Okay, I mean, that's not a huge number. On the other hand, you know, it's one of many aerosols that's it's a problem. It's increasing. Now, again, we mostly fight with black carbon for other reasons. It's a health issue and so on. But black carbon, when we put it into the Earth's atmosphere, it is, in fact, increasing the temperature of the Earth atmosphere system. All right. What about mineral dust? Okay, now mineral dust particles are mostly kind of a natural sort of thing. On the other hand, things like desertification, where we are changing formerly green places into deserts, that increases the amount of mineral dust into the Earth's atmosphere and so on. Mineral dust is really, really fine stuff here. We're not talking sand. We're talking something finer than like talcum powder. This mineral dust particles are generally produced mainly by the disintegration, the right word is, of aggregates following the creeping and saltation. Oh, let me just show you what that is. Hold on. Here's a better slide that kind of illustrates. The surface there is made up of grains of sand that are sort of cemented together with finer silts. This can be literally as in like the surface of like a dry lake or the sandbars on a river or something like that. Or it could just be a thin crust at the surface of the soils over the desert or whatever. But it's usually a little bit cemented together with finer dusts. Then when the winds blow, larger grains of sand start to tumble across the surface of that crusty ground, and they break it up into really, really fine pieces, finer than talcum powder. Very, very fine little pieces that are easy to loft. The sand itself is too heavy. You can tumble across the ground, you know, but never gets really very high above the ground. The talcum powder fine mineral dust, that's what ends up in the atmosphere. This is primarily in the form of these dust storms that, not sandstorms. Sandstorms are a different thing. Even in a really strong sandstorm, the sand is never lofted more than a few meters above the ground. And never gets very far. But the warm ground can create these plumes of this dust that can get very high into the atmosphere. Some mineral dusts are easy to remove from the atmosphere depending on how water soluble they are. Some are hard to remove from the atmosphere and so on. But by and large, mineral dust is pretty light colored stuff. It generally reflects shortwave radiation from the sun, meaning therefore that it has a total radiative effect. The radiative forcing is negative. The radiative forcing associated with mineral dust is a negative 0.1 watt per square meter. You know, that is the anthropogenic part of mineral dust, okay? Like ways in which we've changed the, you know, desertification and construction sites produce a lot of mineral dust, things like that. Okay. Actually, it's not a small amount. about 20% of the total mineral dust in the Earth's atmosphere is considered to be anthropogenic due to like land use and poor agricultural soil processes, draining lakes, road construction. A lot of the air quality issues, for example, around Beijing are often due to construction sites and so on, where winds pick up a lot of these mineral dust. Wow, there's a whole bunch of different kinds of aerosols. They all do different things, and if we added them all up for all those aerosols together, the direct radiative effect is to actually result in a net cooling. Yeah, some of the aerosols were absorbing like black carbon, some were reflecting like mineral dust. If you added them all, the sulfates and so on, if you add them all up, you end up with a net effect where the aerosols are working to cool the climate. They have a radiative forcing of about negative 0.5 watt per square meter. In fact, there's folks who say that we should be exploiting that. In fact, the climate system kind of is exploiting that. It's a phenomenon that goes by the name global dimming. You may have heard this term before. Global dimming is about the fact that aerosols that are in the Earth's atmosphere, aerosols of anthropogenic origin, have a net negative radiative impact. Less shortwave radiation from the sun makes it stays in the Earth atmosphere system, more of it gets reflected out. The sky, less radiation from the sun, less shortwave radiation from the sun is making it to the ground because of us. That kind of partially cancels out the global warming due to greenhouse gases. That isn't necessarily a bad thing, well, at least from a very cold and calculating sense of climate change. But most of those aerosols that we're putting in there are not such good things for health reasons. The sulfates, for example, lead to acid rain. The black carbon leads to various lung issues and so on. Most of them are things we are trying to get rid of. In fact, that could potentially be a big problem. But we will see more about that later. Let's answer a couple quick questions before we move on to part 4. Question 5. Mineral dust aerosols in the atmosphere have a blank radiative forcing on the atmosphere, positive or negative, meaning that they act to blank, cool or warm the planet. What's the role of mineral dust aerosols? Make a choice from those 4 options and get a little feedback before you move on to question 6.